Good morning to everyone. Today we are going to learn about the semiconductor. In last class we also started to learn about semiconductor because I have mentioned several times that semiconductor is a very important part of the science, and especially those who works with computers, different types of devices, electronic engineering or many other science people who work with different electronic devices. They need to understand very well about the semiconductor, and most of the time they need to prepare different semiconductors. So if they do not know very well about the semiconductor or how we can prepare different types of semiconductor or different junctions, then it is very difficult to understand or to prepare a new and perfect one. Making a new one or very good one, that is very important, because sometime you need to develop your device. In that case you need to do some research that how I can develop my system or how I can improve the quality of the device. In that case you have to understand most of the semiconductors or what types of material you can use in semiconductor or different junctions. So today I have taught you about the intrinsic and extrinsic semiconductor in the last class, and today we will focus on p type semiconductor, n type semiconductor, and if I have enough time then I will discuss something about the pn junction and also np junction. But pn junction, that would be enough because we are going to learn based on chemistry, so we are not going to discuss too detail. However, we have lot of or very large syllabus, so we need to cover up. So today is my 17th lecture. However, we are just about at the end of third chapter, so I have more 8 chapters. That is very difficult. So however, I will try to cover up all of them. Let's start with the intrinsic and extrinsic semiconductor. Though I have mentioned in the last class, just I will go a little bit faster for this. So intrinsic semiconductor is the pure semiconductor. That means if there is nothing inside doped, that means no external material inside the semiconductor, in that case we will consider it is intrinsic semiconductor. What can be the examples? Pure silicon, pure germanium or pure boron, or these types of some metals, or sometimes some oxides can be considered as pure semiconductor. But what about the extrinsic semiconductor? Just as we have mentioned about the intrinsic semiconductor, that means no dopant or no other thing we are adding. So extrinsic semiconductor, it should be something. It can be some metal or some other element or atom we are adding in different mechanism just to increase the conductivity of that semiconductor or pure semiconductor. Actually, the pure semiconductor is a very poor conductivity, having very poor conductivity. However, if we add some dopant depending on our interest, that means most of the time we add either the 3 valence atom, the atom having 3 valency or atom having 5 valency. That means 1 electron more or 1 electron less compared to the pure semiconductor. That means if we have a pure semiconductor, all the atoms in the intrinsic semiconductor have 4 electrons. So half filled, or the there we need at least 4 electrons to share, or 4 electrons need to be donated to combine with other element. However, for conducting electricity or heat we need some free electron. So if we have a pure semiconductor, we do not have the free electrons. Then if we add some impure or some dopant, like as the element having 3 valence electrons or 5 valence electrons. In that case, if we add 3 valence electrons by replacing one pure semiconducting material, that can be silicon or germanium, in that case we can have one extra hole. That means if we add 3 valence electrons, so the atom having 3 valence electron, then we should have 4 electrons if we had one pure semiconductor, or that means one silicon atom. But we have now 3 valence electrons having maybe aluminium or something like this. So in that case we have 3 valence electrons instead of 4. Therefore we have a deficiency of electron. That means that deficiency can collect or take one electron from other something. That means we can consider that the deficiency of electron as a whole. Therefore the electron can be taken to that hole from some outside source. Therefore the electron or electricity can be transferred through the doping substance or doped semiconductor. By similar way, if we add some 5 valence electron, 5 atom with 5 valence electron, in that case we can have one extra electron instead of 4 electrons in the atom. Therefore we have one extra electron which can be acting like as free electron, because we have all other atoms have 4 electrons in the outside, and therefore now we will show what types of how we can prepare the semiconducting material by doping or any other way, or what types of element, what are the structure. So just one another thing, and extrinsic semiconductor, mainly the dopant provide the charge carriers. Already mentioned that if we add extra atom, that can be 5 valence or 3 valence. So 3 valency or 5 valency, that can be. So in case of pure semiconductor, we do not have the capacity to conduct electricity because we do not have free electrons. But in case of dopant, if we add dopant, in that case either a free hole or a free electron is available. Therefore that the dopant or the impure element what we are adding, that brings the charge carrier. If we do not have the charge carrier, in that case no electricity or very poor electricity or electron can be conducted. Therefore we are increasing the conductivity by adding some dopant, and therefore we are mentioning the extrinsic. In an extrinsic semiconductor, mainly the dopant provide the charge carriers. The doping agents used are of two types. You are familiar, an electron donor and an electron acceptor. So one electron donor, that means it has one extra electron, and electron acceptor, it has one deficient of electron compared to the nearby neighbors. Therefore so electron donor, that can be an atom having 5 electrons in the outermost shell. So those elements who have 5 electrons in the outermost shell, in the periodic table either group 5 or group 15. So group 5 or group 15, like as phosphorus, then nitrogen, or like this. So any element having 5 electrons in the outermost shell, they can have 5 electrons, so they can donate or they can share one extra electron to the crystal. So the electricity can be conducted by using that free electron. And electron acceptor, just atom having 3 valence electrons, or outermost electron has only 3, or outermost shell has 3 electrons. So that can be like as aluminium or some other boron or aluminum, these types of elements. So based on what types of elements we are adding to the pure semiconductor, the semiconductor are classified into two types, p-type semiconductor and n-type semiconductor. So p-type semiconductor and n-type semiconductor. Now we will learn about the p-type semiconductor. So a p-type semiconductor is a semiconductor when a trivalent. So previously I have mentioned in two different way, that electron donor and electron acceptor. So electron donor, who will donate those atom who has 5 electrons in their outermost shell. Therefore they can donate one extra electron to the crystal. Therefore that electron will be used as a free electron. Therefore that can be conducted as electron donor. So electron donor, how it is can be, if it has 5 electrons. But in case of electron acceptor, it need to have 3 electrons in the outermost shell. So if we add one impure atom having 3 electrons in the outermost shell, or 3 valent electron or 3 valent impurity, if we add an atom having 3 valency as a impurity in the pure semiconductor, then it is called as p-type semiconductor. So a p-type semiconductor is a type of semiconductor when the trivalent impurity is added to an intrinsic, that means pure. The trivalent impurity is added to an pure or intrinsic or pure semiconductor, silicon or germanium. That means this is our pure or intrinsic semiconductor, 100% pure. That means there is nothing impurity. So the band gap for these types of elements is around 1, or in last class you have mentioned some 1.227 something like this, or 1.12. So that p-type semiconductor, that means if we add an element with trivalency, in that case the conductivity. So what are the elements we can add? Trivalent element such as boron, gallium, indium, aluminum, etc. that can be added in the pure semiconductor, and these types of element has 3 electrons in the outermost shell. So they can have one hole or one empty space to take one electron. So if we apply some potential difference, then one electron can come to that space. So there some flow of electron can be generated. Therefore we can have a p-type semiconductor. So ordinary semiconductors are made of materials that do not conduct. Ordinary, that means like consider as pure semiconductor or intrinsic semiconductor, that we are mentioning like as ordinary semiconductor. Ordinary semiconductors are made of materials that do not conduct or carry an electric current. Do not carry current very well, but are not highly resistant to doing so. It do not conduct very well, but they are not highly resistant. That means if you change the condition, in some sense, if you change the condition in some extent, then it can flow electron. So that means it is not highly resistant. That means something, if you has highly resistant, that means if you do any change, most of the time it do not have any property changing. So those who has very high resistance, they do not conduct electricity at all. So ordinary semiconductors, they have or they do not conduct electricity or current very well. However, if you change some properties, like as if you increase the temperature, or if you put some extra material inside it, so in that case it can easily transfer electron or conduct electricity. So it do not conduct very well. That means ordinary semiconductor, they do not conduct very well at room temperature or naturally. However, they do not resist highly, or they do not uh, remain the same if you change the property very little. Just like as if you add some dopant or if you increase the temperature. So for the semiconductor, if you increase the temperature a little bit, in that case the conductivity of that semiconductor, that means pure semiconductor, can be increased. So at normal temperature or room temperature or very low temperature, the pure semiconductor do not conduct very well. However, it can conduct a little bit more or better if you change the property by little, or if you change the state or temperature, pressure or whatever something. So if you change some conditions, in that case you can have the conductivity little bit higher compared to the initial stage. Okay, now here is our structure. That means I have mentioned that to prepare a p-type semiconductor, we need to add a trivalent atom by replacing one. If we consider here was a silicon, if we consider there was a silicon, so all the silicon atoms has 4 electrons in the outermost shell. So each silicon is bonded with nearby 4 silicons. If we consider this is a silicon, this is pure semiconductor we are considering. So if we consider pure silicon here, that means this is pure semiconductor. In that case we do not have any other impurities. Let us consider like this way. So all the semiconductors or all the silicon have 4 electrons in the outermost shell. So each silicon is bonded with 4 different silicons by sharing 4 electrons. So this silicon is sharing 1 electron to this one with this one with this, and this one with this. So all the electrons are shared. That means all the electrons are bonded to each other. So there is no free electron. So it is very hard, or mostly do not conduct electricity or conduct current. Now if we replace one silicon, if we replace one silicon with a trivalent boron or any other atom having the trivalency. So let us consider we are replacing one silicon with a boron. That means boron has 3 electrons in the outermost shell. Therefore what will happen? Just we are replacing one silicon here. Now this is our boron. So boron has 3 electrons. So it can have maximum 3 bonded or 3 bond with 3 silicons. So this boron can form one bond with this silicon, this one can form one, this one can form another bond to this silicon, but still there is a silicon right other side, so it is not bonded to the boron. So what happens in that case? There is a free hole. That means it do not have electrons, so empty space. So if the boron has 3 electrons, so it can form 3 bonds with the nearby 3 silicons, and it has one empty space where we can add 1 electron from the outside. So from anywhere, or from outside we can add 1 electron at the free space, which is considered as hole. So if you apply some potential difference with the that would be like as a crystal. So if we apply some potential difference in between the crystal at 2 different ends, in that case, so 1 electron can come here. So if you have some repeating unit like this, this is one unit what we are considering, one boron and then some other silicons outside. So if you have some other boron atoms and some other repeating units, in that case they will have lot of free holes. Therefore when you apply the potential difference, that means when you apply electron to the crystal, in that case the electrons can come to the nearby free hole and then that electron, so in that case boron will have 4 electrons, but boron cannot have 4 electrons because the boron has only 3 electrons in the outermost shell. Therefore so that free hole will be transferred to the nearby atom, so that way the electron can be transferred. So that is the way how we can prepare a p-type semiconductor and how the p-type semiconductor can flow electron or conduct electricity or current. So let's see what I have discussed here. An electric current occurs when electrons move through a material. In order to move, there must be an electron hole in the material for the electron to move into. So we need to have some free hole or free electron to conduct current or electricity. So there must be an electron hole in the material for the electron to move into. A p-type semiconductor has more holes than electrons. Here we have one hole and we do not have free electrons. In this case, in this silicon, this electron is not free. You may consider this electron is not bonded. However, the silicon has 4 electrons initially, so these electrons are bonded or bound to the silicon atom. So it do not have any free electron, neither this silicon, neither this, neither this. So none of the silicon has the free electrons. If it had free electrons, then we don't need to add any impurity. So it do not have free electrons, it has free holes because we have added one trivalent atom inside the silicon or pure semiconductor. Therefore a p-type semiconductor has more holes than electrons. This allows the current to flow along material from hole to hole. So I have mentioned that from hole to hole it can transfer the electron, so from hole to hole, but only in one direction. So in only one direction, that means if you apply the potential difference in one direction, then it can flow electron. To make a p-type semiconductor, extra materials like boron or aluminum are added to the silicon. Already mentioned that any material having 3 valency or outermost shell has 3 electrons, that types of elements or materials can be added to make the p-type semiconductor. These materials have only 3 electrons in their outer shell. When the extra material replaces some of the silicon, it leaves a hole. So if we replace one silicon with the trivalent atom, in that case there will be one free space, so that can act as a hole and that will be liable to transfer electron. When an extra material replaces some of the silicon, it leaves a hole where the 4th electron would have been if the semiconductor was pure silicon. Therefore if the pure silicon was there, to discuss p-type semiconductor, I have first mentioned that we have all of them are silicons, so we can easily understand that we had one electron here. But if we replace one silicon by one boron, in that case we do not have one electron here, therefore we have a free space, so that can be considered as hole, and that hole can transfer electron from the outside to the nearby hole, so in one direction it can transfer. Now we will discuss about the N-type semiconductor. So what is N-type semiconductor? Just opposite, as already we have mentioned about the P-type semiconductor. Now we can consider about this N-type semiconductor. That means if a pure semiconductor is doped with a pentavalent atom. Pentavalent, that means if an atom has 5 electrons in the outermost shell, then we can consider that is a pentavalent atom. And if we consider that previously I have mentioned the structure of pure silicon or pure semiconductor, so I am not going to discuss again detail. So now we had a silicon here, that means we had 4 electrons. Now if we can replace one silicon, by one 5 valence atom, like as antimony or bismuth or something like this, or even phosphorus. So if we can replace one silicon by a pentavalent atom, that pentavalent atom previously we had the structure so that the antimony can form bond with 4 silicon having 4 electrons shared. So one here, one here, one here, one. So one antimony can share 4 electrons to make bond with the nearby 4 silicons. However, antimony has 5 electrons. So that extra electron cannot be shared to any other silicon. Therefore, that extra electron remains nearby silicon, or it is a free electron, and that can move around the crystal. So if we apply some potential difference, in that case we can have some flow of electron in certain direction, because we have one extra electron for a antimony atom. Now if you have so many or many of antimony or pentavalent atoms inside the doped substance or semiconductor, in that case you will have a lot of electrons. Therefore that can be used to transfer the electricity or conduct electricity. So N-type semiconductor, one silicon atom replaced by a antimony. So not only antimony, you can add any pentavalent atom, but all of them will not have the similar or same property. I should say similar property they will show, but not the exact or same property, because if you consider that the conductivity increases if we replace one silicon by one antimony, in that case the conductivity for that semiconductor can be increased, let us consider 1000 times. But if you add some bismuth, in that case the conductivity can increased by 10,000 times, maybe. Exactly I do not know how much it will be increased. However, if you add different elements, different pentavalent elements, so in that case, or different trivalent elements, in that case the conductivity will increase a certain amount, but not always same for if you replace one atom antimony, if you replace with phosphorus, or if you replace with a bismuth. In that case the conductivity or the property will be changed little bit. Why it is changing? Because if I say the size of the phosphorus, if you consider the size of the phosphorus atom is smaller compared to the antimony or bismuth, therefore the electron will reside little bit closer. If you consider for phosphorus, the electron will reside closer. So the property, if we replace one silicon by antimony, that case the crystal structure can be distorted little bit more compared to if you replace one silicon by one phosphorus. So the characteristics of that material of that semiconductor will be changed little bit more if we dope with different material. So we have 5 valent atom. However, if we replace one atom by other, in that case the valency or the crystal structure can be changed quite a bit. Therefore, that will give you similar trend by increasing the conductivity, but not the exact amount what the conductivity is for if we replace with the antimony, or if we replace with phosphorus, or if we replace with bismuth, that will be different. So you need to know, if we add one antimony, how much the conductivity can be increased, so that you can design your device so that if we use these types of semiconductor, then we can prepare these types of junction, then our device need that mass electricity to conduct. So you need to think about that characteristics for that device. Let's see, an n-type semiconductor is made by adding an impurity having 5 electrons in the outermost shell to a pure semiconductor such as silicon or germanium. So this is the main word, just how we can prepare an n-type semiconductor. This is our pure semiconductor, silicon or germanium. So if we add a pentavalent atom, so it has 5 electrons in the outermost shell. So if we add these types of element to the pure semiconductor, in that case we can have a n-type semiconductor. The impurities used may be phosphorus, arsenic, antimony, bismuth, or some other chemical element having 5 electrons, but actually most our periodic table have these types of these elements: phosphorus, arsenic, antimony, bismuth. Or sometime if you add some impurities, maybe some oxides, that also can be, but maybe not good as that these types of elements, phosphorus, arsenic, antimony. So if we add some pentavalent atom to the pure semiconducting material or semiconductor, in that case we can have a n-type semiconductor. They are called donor impurities. In the previous slides I have mentioned that donor semiconductor or donor element and acceptor element. So donor element, that means those who have one extra electron that can donate an electron, that are known as donor element or donor impurities. The impurity is called a donor because it gives a free electron. It gives a free electron to a semiconductor. So it has 5 electrons, so it can donate one extra electron to the nearby, or so it is considered as donor impurities. The purpose of doping is to make more charge carriers. So why we are doing doping? That is our target, to increase the capacity or conductivity for the material. The purpose of doping, this is to make more charge carrier or electron wires available in the material for conduction. The final material is a lot more conductive than the original silicon or germanium. So if you dope with a p-type or n-type material or donor or acceptor impurities, in that case the conductivity of the pure material increases quite a lot. So now we will learn about the p-n junction. What is p-n junction? We have learned about the p-type semiconductor and n-type semiconductor. So if we attach a p-type semiconductor and n-type semiconductor together, in that case we can have a junction. That means the join, the p-n junction is a boundary or interface. This is an imaginary boundary. This is not actual. This is an imaginary boundary. A p-n junction is a boundary or interface between two types of semiconductor materials. So this is p-type semiconductor and this is n-type semiconductor. That means in this material or in this semiconductor we have free hole and here we have free electrons. So if you attach or if you join a p-type semiconductor and n-type semiconductor, in that case now if you connect or if you apply some potential difference to the ends, so this is one end, it is connected with the potential source, cathode and anode. So if you connect or if you apply some potential difference, in that case the free electron from this n-type semiconductor, because we know this n-type semiconductor has a lot of free electrons and it has lot of free holes. So what will happen if we apply or if you apply some potential difference, in that case the free electrons of the n-type semiconductor will try to move this way towards the hole, and the hole in the p-type semiconductor that will try to move towards the right, but actually the hole do not flow, the electrons flow. So a p-n junction is a boundary or interface between two types of semiconductor materials, p-type and n-type, inside a single crystal of semiconductor. This is overall, actually this is a single crystal. So we are making first one p-type semiconductor and this is another n-type semiconductor, and then we are joining by some process that can be several way. In the next slides I think I should mention here. The p-type positive side contains an excess of holes. Already mentioned that p-type has excess holes and n-type semiconductor has excess electrons in the outer shell of the electrically neutral atoms there. This allows electrical current to pass through the junction only in one direction. So the hole, it should be transferred to this way and the electron should transfer like this way. So only one direction the flow can be. So how we can define the current? The flow of electron is known as current. So if we apply potential difference, then the free electron can go towards this or p-type semiconductor. In that case we can have a flow of electron, that means we can have a current. So the p-n junction is created by doping, for example by ion implantation. So there are several ways to prepare a p-n junction. How we can make it? That is ion implantation. That means if you have a crystal, then you can penetrate some other ion by, if you have a very high force or high source electron or ion, in that case, so you have a certain crystal. Let us consider this is my mobile, so this is one crystal surface. So if you have some high energy electron, so in that case you can pass or you can insert the electron to the surface by ion implantation. That means this is the surface, so you can pass electron to the surface by high speed electron or high speed ion. Diffusion of dopants. What is dopants? Diffusion, that means if you melt, the dopant and then you can diffuse, you can combine the dopant into the pure silicon or pure semiconductor. That way you can prepare the p-n junction. Or by epitaxy. Epitaxy, this is a natural growth mechanism, crystal growth mechanism. So you can generate or you can prepare some crystal in natural way. That means you have some liquid or some mixture of solution. In that case in naturally you can keep for settle down and then you can generate crystal by some time, but that is very difficult and you cannot control the size and shape of the crystal in that way. In that case, after preparation, the size of the crystal you need to cut into your smaller pieces or whatever, but making bigger crystal is very difficult for this methodology and you cannot control the size or shape. PN junctions are elementary building blocks of semiconductor electronic devices such as diodes. So to prepare any device, different types of device, diodes, transistors, solar cells, LEDs and ICs, lot of semiconducting device you may need. So to prepare any types of devices like as diodes, transistors, then solar cells, LED and ICs, so you need to prepare a PN junction. So to prepare a PN junction you must need to have a p-type semiconductor and n-type semiconductor, and then you need to combine the two semiconductors or two type semiconductors together so that you can have a junction. So to make any device, what we are considering electronic devices, at least to make any electronic devices we must need to have a PN junction or any junction. For example, a common type of transistor, the bipolar junction transistor, consists of two PN junctions in series in the form of NPN. This is one junction, NP junction and PN junction, or PN junction and NP junction. So these are different types of arrangement or position. So these are different types of arrangement that we can have our junctions combined to make our devices from, while a diode can be made from a single PN junction. So you can prepare a diode by using only one PN junction, but in case of transistor, bipolar transistor, you must need to have a series of a two PN junction in series like as NPN or PNP, these types of. So that can be considered as forward bias and reverse bias. So I think I am not going to discuss about that detail because this chapter do not cover all of them. However,